let's give this a go. Welcome, everyone. Oh, great, my slides don't fit on the screen. I'm just going to have to move them around every now and then. Okay, so welcome. I'll just introduce myself. I'm Kyle. I'm a visitor here this year. Typically, I'm over at Reed College in Portland, Oregon. And today I want to tell you about homotopical combinatorics. So this is a departure from the work that I've done in the past, which has also been situated in homotopy theory, and has also been focused on getting concrete answers to problems. Previously, I've worked in motivic and equivariant homotopy theory focused on spectral sequence computations. Today, I'm going to work in abstract homotopy theory, the world of Quillen model structures. And instead of doing spectral sequence computations, I'm going to count. We're going to get some numbers, and that's the primary goal here. So this is joint.
That intersection drawn to scale?
That would be good for my grant applications if it were. Right, so this is work that's joint with some wonderful collaborators. Scott Balchin at Max Planck. Evan Francher is a grad student at Kentucky, previously at Reed. Usman is previously at Reed, took a gap year. He's on the market for grad programs this year. If only I knew someone involved with graduate admissions. Ethan McBrow is a senior at Reed, and he'll also be applying to grad school. Peter Marcus is at Tulane, and Helga Osorno was here last week giving the topology seminar, and is also my collaborator and colleague at Reed. Weihang Chen, he told me this is him biking across Tibet. He's off in China doing computer graphic stuff these days. Constanza Reutzheim is at Kent University in the UK, and Riley Waugh is now a talented educator who was previously at Reed. I would love to add your faces to this slide. I think one of the highlights of homotopical combinatorics is its accessibility, and there's also a lot of fruit. I want to say that it's low-hanging. We haven't gotten to it yet, so we don't really know. But I think there's a lot to think about and play with here. So do reach out if it's something you might want to talk more about in the future. Before we get into homotopy theory and stuff, I want to pose a warm-up problem. This is a special sort of warm-up problem. If you solve it before the end of the lecture, I will purchase a beverage of your choice for you. So here's a game. We've got a grid. It's m by n. It starts at 0, 0, and it goes up to m comma n. This grid is 7 by 4. And we've got a bunch of unit length matchsticks. And we're going to place them on the board in either horizontal or vertical configurations between the vertices. And there are some rules, which are a little cut off here. But whenever we place a vertical, we have to have all verticals to its left. Okay? And whenever we place a horizontal, such as this one, we have to have all the horizontals below it. And then finally, to make things extra tricky, we never allow ourselves to have just 3 sides of a square. 1, 2, or 4, fine, but not 3 in any rotation. So you might imagine that we could change this configuration, for instance, just by adding one here and then adding everything to its left. But that would, in fact, not work because we would have this side omitted out of the 4. So that's a legal configuration of matchsticks. And your challenge problem here for the start of the lecture is how many legal matchstick configurations are there on the m by n grid? Okay. A follow-up question is what did you just count? if you succeed. And at the very end today, I will answer both of these and give what I think is a really cool formula for this, and also tell you a homotopical significance to this count. Okay, now let's do some category theory. So what are we counting? We're counting so-called Quillen model structures. These are 3 classes of morphisms on a category: weak equivalences, fibrations, and cofibrations. And once we have those 3 classes, we're then permitted to define the acyclic fibrations and the acyclic cofibrations, where we just take the intersection of fibrations or cofibrations with the weak equivalences. These have to satisfy 5 axioms. The first one is that the category is complete and co-complete. That means that it has all limits and co-limits with respect to small categories. Second one, importantly, these weak equivalences satisfy 2 out of 3. So if we've got composable morphisms F and G, and F, G, the composite, if 2 of those belong to W, then so does the third. So it's closed under composition, but there's also 2 additional conditions. The third one says that W, F, and C are closed under retracts in the arrow category. That's a technical condition that will be less important later, so I won't get into it. The fourth one is a certain lifting condition on cofibrations and fibrations, which I will define later. And then finally, we have this factorization axiom. It says that every morphism in our category can be written as a cofibration followed by an acyclic fibration, and also as an acyclic cofibration followed by a fibration. So this structure is due to Dan Quillen. He has a 1967 text that introduces these called Homotopical Algebra, and that indeed was inspiration for the title of the stuff I'm working on and presenting today. All right, so let's do that. All right, here's what we're going to do. Given some co-complete category C, we would like to classify and enumerate all of its model structures. So Quillen introduced these in order to do homotopy theory, in order to give a controlled model for inverting the weak equivalences. And this is a really successful way to do so, and it's how many contemporary homotopy theorists build the categories in which they work. But there's been very little attention paid to this enumeration problem, just like how many different ways could we do it? What are the possibilities, the landscape? Now, some things are known already, or were known before. A folklore result, which was elaborated on by Tom Goodwillie and also Toby Bartle and Omar Antolin Camarena, says that there are exactly 9 of these model structures on the category set. Bartle and Antolin Camarena have a nice write-up of this on Omar's website that you can check out. Outside of this theorem, I know of no classification results for all model structures prior to this work. Today, one of the theorems I want to tell you about, due to Scott Balchen, myself, Angelica Osorno, and Costanza Reutzheim, is that if we're dealing with the category that I'll call brackets n, so this is generated by arrows from 0 to 1, 1 to 2, etc., up to n minus 1 to n, then you just kind of insert all the composites that you need. If we're looking at model structures on that very small, somewhat contrived category, then there are exactly 2n plus 1 choose n of those. Wonderful combinatorial number. And moreover, if we want to specify the homotopy category of brackets n, say that it's brackets k for some fixed k between 0 and n, in that case, there will be precisely this many of them. And I won't read that formula out. But again, it's a very explicit, closed formula for the number of such model structures. And what we'll see about midway through the talk is that we can actually count them in terms of certain classic combinatorial lattice paths. I'll say more. Some more recent work by myself, Scott Balchin, and Ethan McBrow says that in this case, the model structures are actually in bijection with other combinatorial structures, nice principled bijections, with a certain class of triangulations, ways of subdividing the triangle into more triangles, a certain class of colored trees, and also a certain class of intervals of non-crossing partitions. So special flavor of partitions, and then a pair of them where one is a refinement of the other. So this will give a nice conceptual way. In particular, these trees, these are very easy to write down, and we have kind of a cookbook way to then take a tree and transport it into one of these model structures where we've got, oh my goodness, all of these arrows. We've got to identify particular ones as weak equivalences, fibrations, and cofibrations. Great. So in order to make sense of this, we need to talk about that lifting axiom that I omitted earlier. And I'm going to give an alternate presentation of model structures that will be beneficial for our approach. So let's imagine that we have a square like this. The objects don't matter, so I'll leave them out. But we have these vertical morphisms, I and P, linked by horizontal morphisms, F and G. And we'll say that I has the left lifting property with respect to P when, for any such diagram, we can factor it via H. In this case, we'll use this cute little notation here. Note that this box with a slash looks a lot like this box with a slash to denote that I lifts against P. Great. We'll also define these upper box slash notations. Upper box slash M is the stuff that lifts on the left against everything in M. M upper box slash is the stuff that lifts on the right of everything in M. So with these definitions in place, a weak factorization system on our category is a pair of morphisms, L and R, L inside of the morphisms of C, R in the morphisms of C. And it satisfies the following properties. So first off, we have factorization of morphisms into first do a left morphism, then do a right morphism. We have that L lifts on the left of R. And finally, we have closure under retracts in the arrow category. So that's a weak factorization system. And before we get to model structures, I want to tell you what a pre-model structure is. So this is an idea due to Reed Barton. So in his thesis, he's interested in building sort of a two-category of model structures, but those don't admit limits. So he comes up with this weaker notion. And all it is a pair of weak factorization systems that are compatible. Okay, and in this setting, we'll call AF the anodyne fibrations and AC the anodyne cofibrations. So we're replacing the word acyclic with anodyne. And we don't call them acyclic because this isn't necessarily a model structure. If we have a model structure, we can produce a pre-model. And in this scenario, the weak equivalences are the things that are acyclic fibrations after acyclic cofibrations. But if we build this for an arbitrary pre-model structure, this class down here might not satisfy 2 out of 3. Okay, that's how this can fail to be a model structure. But Joyal and Tierney tell us that in fact, the model structures are we just have to rectify that one issue. So if AF compose AC satisfies 2 out of 3, then we really do have a model structure. And this is how we'll think of them in this setting, rather than WF and C satisfying these 5 conditions. The upshot here is that premodel structures on C are intervals in a poset of weak factorization systems, where we say that LR is less than or equal to L prime R prime when R is contained in R prime. These intervals then correspond to model structures if and only if this R compose L prime has 2 out of 3. Okay, and I said we want to do some counting, but this is still too hard, right? So giving all weak factorization systems on some co-complete category, very challenging. But maybe if we look at a rich but very specialized class of categories, we might have a fighting chance. So here is one such class of categories, quite constrained, but also quite beautiful in its own right. We can look at complete lattices. So this is a lattice in the sense of the theory of partially ordered sets. So that means that it has this relation, which is reflexive, symmetric, not symmetric. It's reflexive and it's transitive, and what's the other property of a poset? Hang on, I swear I know this. Anyway, a poset that has meets and joins. So that means that it has infima and suprema. There are a ton of examples of these. So we could have a chain. It could be just 0 less than 1 less than n. Here I've drawn the Hasse diagram for that. So in this case, I'm just drawing the covering relations. Covering relations are sort of the minimal relations between distinct elements. When we have this relation and this one, transitivity says we also have this one, but I'm not going to draw that. We could take Boolean lattices. So these are these kind of hypercubes, brackets 1 to the n, but you can also think of them as subsets of a set of size n. Subgroups of group G, that forms a lattice. The meet is intersection, and the join is subgroup generated by. Here's the subgroups of the symmetric group on 3 letters. And then there are more exotic things, the Tamari lattice, the Craveris lattice. Those will both show up later. I've drawn a picture of the Tamari lattice here. The topologists in the room might also know this as the one skeleton of the isosahedron, built out of full planar binary trees. Okay. Now, a lattice was a special kind of poset. We can also think of that as a category, where we just take our poset and we say the objects are the elements of the set. And there's a unique morphism from x to y if and only if x is less than or equal to y in the category. Composition is then basically transitivity in the poset. All right, and notice here, it's a little off the slide, but the category P is co-complete if and only if the lattice is a complete lattice. So now we can state a sort of refined goal, which is to enumerate and determine the structure of these weak factorization systems. Then look at intervals amongst weak factorization systems. Those are premodel structures. And then amongst those premodel structures, identify the Quillen model structures, where AFAC satisfies 2 out of 3. Okay, and I've got a little note down here about exactly what I mean by intervals, but they are just these pairs where the first is less than or equal to the second. Okay, we're going to get an assist. And this, I think, is one of the true surprises in this story. To determine these weak factorization systems, we can actually think about n-infinity operads. what in the world is that? So in-infinity operads are these objects introduced by Andrew Bloomberg and Mike Hill. And they introduced them in the setting of thinking about equivariant ring spectra. So these are ring objects in some equivariant spectrum category. So a place where you're doing equivariant stable homotopy theory. And they arose to prominence in Hill-Hopkins-Ravenel's solution of the Crevert invariant 1 problem. They needed to be able to sort of build nice equivariant ring spectra in order to do the computations that were important there. But Bloomberg and Hill observed that these don't have a lot of the properties that we expect of E-infinity ring spectra, the non-equivariant case. So you know that you have sort of naive E-infinity operads in this equivariant world and ring spectra with respect to them. But you often also have additional norm maps. And it's nice when you've got all possible norm maps, these sort of multiplicative maps that are indexed by subgroups. In-infinity operads are a way of keeping track in your ring spectra of exactly which norms you have. And the somewhat surprising thing is that when you do various localization procedures on equivariant ring spectra, it can destroy some of those norms. And so you've got to be really careful if you're doing something like equivariant derived algebraic geometry, whatever that means. Suddenly, you know, many of your objects carry additional structure, but that structure changes as you pass to different localizations. So Bloomberg and Hill invented these to think about those kinds of problems. And then one of Mike Hill's postdocs, along with a slew of other people whom I apologize for not listing here on the slide, thought about the homotopy theory of these operads. And they deduced that they could actually be encoded in a tiny little bit of combinatorial data on the subgroup lattice of the group of equivariants. The thing that we're working towards is that these transfer systems, for reasons that are quite surprising, will actually encode weak factorization systems. They also encode this important stuff about equivariant homotopy theory. What are they? So a transfer system on a lattice, such as a subgroup lattice, is a transitive relation R on the poset, refining the original relation. So meaning that when A is R related to B, then A is less than or equal to B. And it needs to be closed under restriction. So that says that if we have X R related to Z and Y less than or equal to Z, then while we have every right to form the meet of X and Y, which is necessarily less than or equal to X, and closure under restriction says that it's also R related to Y. Okay, now in the setting of equivariant homotopy theory, you also need to track conjugation action on the subgroup lattice. And in that case, you would also require R to be closed under conjugation. That's not a condition if G is abelian. And when I'm thinking about just general posets, I'm not going to have a conjugation action like that. So I'm just going to ignore that condition. But what Francher, Osorno, Chen, Wah, and myself realized is that when P is a lattice, there is actually an isomorphism between transfer systems on P and the weak factorization systems on P. It turns out that these special relations that are closed under restriction are exactly those things which can appear as, I see what happened, which can appear as the right sets in a weak factorization system. So this was really surprising. And it arose because we were just trying to do equivariant homotopy theory. We were trying to enumerate some transfer systems. And we started playing around with it on chains, and we got a well-known sequence that I don't want to spoil later. We started playing with it around with it on like a chain cross an interval. So n cross 1, a little ladder poset like that. And wrote a computer program, got some numbers, plugged it into OEIS, and lo and behold, it matched the number of weak factorization systems on the same poset. So then it was kind of game on, like, is this a general phenomenon? And it turns out that it is, and we were able to prove as much. And it's one of these things you would never expect, but once you write down the appropriate assignment, it's not terribly challenging to check. What happens, here's my spoiler sequence. When we're working with a chain, it turns out that Balchin, Barnes, and Reutzheim had already enumerated the transfer systems on a chain. They showed that this recovers the Tamari lattice that I showed on a slide a few back. And the Tamari lattice has exactly Catalan many vertices. So the number of transfer systems on this n plus 1 element set is the n plus first Catalan number. So just quick straw poll in the room, because I feel like there might be a lot of homotopy theorists here. Who's thought about the Catalan numbers before? Encountered them? A little bit? Getting a lot of wiggly, wavy. Okay, so then this next slide will be of some use. So Catalan numbers are beautiful combinatorics. They're elementary in the sense that with an ambitious high schooler, you can absolutely get into a lot of this material. I cover it in the first year combinatorics class that I teach at Reed. This is a sequence. It starts 1, 1, 2, 5, 14. I'm going to say if you ever encounter 2, 5, 14 in your work, like just jump to Catalan and see if you're onto something. They satisfy a really nice recurrence relation. This is often the easiest way to identify that you've got a Catalan enumerated sequence. And they enumerate a huge number of structures. So there's a very famous problem in Richard Stanley's enumerative combinatorics book. It's like a single problem with parts A through like double M or something. I can't remember exactly. The answer to every single part is like, here's some structure. What's it enumerated by? Here's another structure. What's it enumerated by? The answer to every single one is the Catalan numbers. He even has a supplement that then gets into like triple. There's so many things. Here are some of my favorite. These planar full binary trees. So you can think of these as parametrizing ways to parenthesitize a sequence. If you've got A, B, C, D, E up here, then you're going to combine these, you're going to combine these, then you're going to combine these because you have this, and then finally do the last multiplication down here. They also enumerate Dyke paths from 0, 0 to NN. So this is a path consisting of unit east and north steps that never crosses this diagonal. They also parameterize non-crossing partitions of an n-element set. I'll have a slide later that defines these precisely, but basically we don't allow, for instance, these two elements to be in the same set if these two are in the same set, because there's some kind of crossing going on there. They enumerate triangulations of an n plus 2 gon by chords, and this leads to a lot of beautiful stuff with like cluster algebras and great combinatorics there, and again, much more. A couple of lattices whose points are enumerated by Catalan numbers are the Tamari lattice and the Creveris lattice. The Tamari lattice its vertices are these trees, and the covering relation is rotation. So if you've got subtrees A, B, and C up here, you can take this subtree on B and swing it around to put it over here. Oh, I'm so sorry. Yes. Okay, now I can't mark on the slide, but B is swinging around there, and that's a rotation. There's also non-crossing partitions, and you can look at refinements of partitions, and that's a nice order. There's a canonical bijection between trees and non-crossing partitions that goes through dike paths. And if you see how the orders relate, you find that the Cravaris order is a refinement of the Tamari order. Okay, that'll be important later. So now we get some low-hanging fruit just by identifying premodel structures with intervals in amongst transfer systems. We see that the premodel structures are isomorphic to intervals in the Tamari lattice. And prior work from the early 2000s by Frédéric Chapeton counted these Tamari intervals. There's exactly this many of them. I won't read that. Shifting this by 1, because we've got this pesky n+1 up here, we find that the number of premodel structures is this translation of Chapeton's formula. And now we can go further. We can try to find the model structures amongst these. And this is the theorem that I mentioned at the start today. There's exactly 2n+1, choose n of them, and exactly this many whose homotopy category is brackets k. The idea of the proof here is to split up the count. So we specify k such that we have this isomorphism of homotopy categories. And then we specify the weak equivalence classes. It turns out that that has to be a partition of 0 to n into a bunch of intervals. And so those intervals are encoded by this sum down here. And then we have to specify a contractible model structure on each of those pieces. And those, it turns out, are the same thing as specifying a weak factorization system on that interval. And so we get this Catalan count on each of those pieces. So all we have to do is check that this double summation of this product of Catalan numbers is this. You can easily have your computer go and say that, you know, this has got to be true. And we found a pretty nice conceptual argument in terms of dike paths. Just thinking of this interval down here as giving you, I wish I could do this a little more easily. It gives you the ways that the diagonal is chopped up in that picture. And so you end up counting the dike paths on an n+1 by n+1 grid where the first step is north. And that's then a relatively straightforward problem to check that that's enumerated by this number. Okay, if you want to get the things where you fixed k, we were rescued by a 1976 paper of Shapiro, where this had been computed in a very different way. All right, so that's where things were about 2 years ago, and now I want to tell you about some recent work that Scott Balchin, Ethan McBrow, and I did over the summer. So we started thinking there's a really big gap between these pre-model structures and the Quillen model structures. The Quillen model structures are very rare amongst pre-models as n gets big. So we'd like to sort of fill the gap in between, find some intermediate where it might be easier to find model structures. And to do that, we introduced what we called composition closed pre-model structures. So these are pre-model structures in their typical presentation where the putative weak equivalences are closed under composition. So not necessarily the full 2 out of 3, but at least closed under composition. And we found some pretty cool mathematics hiding in that type of structure. When we were working with the category associated with a lattice, what we found is that there was a partial order. I'll make it this kind of curly less than or equal to on weak factorization systems that refined less than or equal to the standard refinement relation, and such that we had an interval there in this curly relation if and only if the associated AF compose AC is closed under composition. And moreover, we produced a really nice effective criterion for checking when you had this relation. Because a priori, I mean, this is kind of a pain to check, right? I mean, you've got to produce all these lifts, and then you've got to build all the composites, and then somehow know that that's closed under composition. Well, actually, you can do it strictly in terms of R and R prime and a particular flavor of splitting whenever you have a square. So you can effectively check that on an arbitrary lattice. And when the lattice is finite, we showed that this new relation, curly less than or equal to, is also a lattice. So we have a lattice refining the original lattice, and whenever you have a finite lattice and you take intervals in it, you get a new lattice. So we now know that composition closed premodel structures on a lattice form a finite lattice. This is quite distinct from what happens with model structures. You can produce an ordering square less than or equal to on weak factorization systems such that the pair, the interval corresponds to a model structure. But in that case, what you get is absolutely not a lattice, and I'll just exhibit that by example down here. So these are all pictures for brackets 2, so just 0, 1, 2, really simple. If we look at the weak factorization systems under their standard refinement, then we get this pentagon. And if you're familiar with the associahedron, you might be nodding your head right now that you get those pentagons when you have like 4 terms that you're multiplying in different orders. Now we have this refinement, curly less than or equal to, where you've got the same vertices, but now these are the covering relations. That's still a lattice. Okay. But now, when you pass to the relation where the intervals correspond to Quillen model structures, you get this picture, which is absolutely not a lattice. So for instance, there's no meet of the 2 highlighted elements. Staring at these pictures for a while, you can verify these counts. There are 13 premodel structures, 12 composition closed premodel structures, and 10 Quillen model structures. Okay. We would like to count the composition closed model structures and see how well they do at intermediating between these 2. And it turns out that we recover another well-known story, that of the Cravaris lattice. So for R, a transfer system, I'm going to define a little auxiliary function, pi r. It's going to send I to the biggest j that it's related to, according to the transfer system. And a little kind of aside proposition that we proved a couple years ago is that you get a bijection between transfer systems and non-crossing partitions by just forming the non-crossing partition out of the non-empty fibers of this function pi r. So it's not a lattice isomorphism because the Cravaris structure and the Tamari structure are distinct, but it's still a bijection of sets. And it turns out, delightfully, that when we pull back this refinement Cravaris order on non-crossing partitions and pull it back to transfer systems, that coincides with the curly less than or equal to. Once again, the combinatorialists beat us to the punch. They've already counted Cravaris intervals. That's actually one of the original things that Cravaris did in his, again, it's like a 1970s paper. And the Cravaris intervals are counted by this number. So that's how many composition closed model structures you have. We did go and work out the asymptotics. There's a lot of space in between all of these steps. Big gap between pre-model and composition closed, and another big gap between composition closed and model structures. But still some very curious combinatorics popping up. So it then is the case I mentioned that Chapitone had counted intervals in the Tamari lattice. Those numbers ended up coinciding with some kind of triangulation. And the Cravaris intervals are well known to, their count is well known to correspond with a restricted class of triangulations. So there's a very beautiful 2009 paper by Bernardi and Bonichon that gives explicit bijections between Cravaris intervals, a particular flavor of trees, and a particular flavor of triangulations. And Scott, Ethan, and I had produced this bijection up here. And so we were really curious, well, if we push that into trees or triangulations, where do the model structures fit amongst those? Sorry, that's off the slide again. So here's the particular flavor of triangulation. They're called stacked. You start with a triangle, and you put a vertex in the middle, right? And now at each iterative step, you choose one of the subtriangles and put a vertex in the middle. Okay, and those are stacked triangulations. Here's an example of a non-stacked triangulation. So this was not built in such an iterative fashion. So the arbitrary triangulations with a condition on how many vertices correspond to Tamari intervals, and these stacked ones correspond to Cravaris intervals. Okay, and I'm going to run you through briefly what our constructions look like, just so you have a flavor of it. What did Bernardi and Bonichon do? They said, well, if you've got one of these stacked triangulations, you can give some colors to the vertices. That's red, blue, and green. And then when you drop a new vertex in, you can color it, like here you have this green edge coming in, color the opposite side of the vertex green. And blue's coming in here, so color the opposite side of that vertex blue. If I make it bigger, you can see that the vertices are colored, perhaps. And then as you drop in new vertices, say B here, then, well, it's a red edge because it's connected to the red part of the vertex. And again, we do this coloring according to the opposite of the edge. All right, so we can color nodes that way, and color the edges according to the parent node's color. And then the way that we produce a tree out of that is that if W subdivides some triangle, so for instance, say D here subdivides the triangle between A, C, and the original blue vertex, then in the tree that we're building, we'll connect W to the highest of X, Y, and Z on that tree. So here D, it's subdividing something involving both A and C, but C is higher on the subdivision tree, and so we'll connect it there. That's a recipe, and Bernardi Bonichon show that it is a bijection. From this tricolored tree, we can produce something called an admissibly ordered tree. In the interest of time, I think I won't go through the full method here, but it's a way to ultimately produce trees that look like this. So this is a tricolored tree, and what's special about it is that the red and green edges have certain relations to the blue edges and to each other, and we end up with one vertex associated, spread out in this way. We then get a recipe and I can provide these slides later if you want to look into it, for turning one of these trees into one of our functions, pi r. Now we want two pi r's, pi r and pi r prime, because we're looking for an interval of non-crossing partitions. And the recipe is written down here. And for this particular tree, you get out these values of pi r and pi r prime. And from a function like this, you can always produce a non-crossing partition by taking the non-empty fibers. So here I've written out the full procedure. We start with a tree like this. We produce the pi r and pi r prime functions. And then from those, we produce the non-crossing partition. So those are the purple lines here and here. That just barely fits on the slide. You're not missing anything. And then these are the maximal relations. You then have to generate some new ones in order to get the full transfer system. But this now gives you essentially the acyclic fibrations and the fibrations in a composition-closed premodel structure. Moreover, we can identify exactly which ones of those correspond to model structures. So via these bijections, the model structures correspond to trees that look like this. There's a single red field with a bunch of blue-green trees growing out of it. Okay, and I didn't write it here because it's a little awkward to phrase, but we can also identify which triangulations correspond to model structures. So these are literally the tree, the non-crossing partition, the triangulation, and the full model structure picture that correspond to each other via this web of bijections. Okay, so I've got about 4 minutes left, and I want to finish. We've got to get back to the matchstick game. So has anyone solved the matchstick game during the talk? I will still take you out for a drink. Okay, so matchstick games, little spoiler for the next slide, they're going to count saturated transfer systems. This is a special class of transfer systems. They showed up in equivariant homotopy theory because whenever you have a so-called G linear isometries operad, it induces a saturated transfer system. It turns out that these saturated gadgets, which are those which satisfy 2 out of 3, not every transfer system does that, far from it. They actually, on a self-dual lattice, this is a simplifying condition. I could write a longer theorem here if it wasn't self-dual, but it makes this a cleaner statement if I make that assumption. If it's self-dual, then these saturated transfer systems actually correspond to a bunch of classically important combinatorial structures. First, they have a homotopical significance. They're model structures where everything's a fibration. But then they're also closure operators, they're submonoids, and they're monads. So they have all these different faces. And these problems, these enumeration problems, have been well studied in literature, and they're interesting and hard. So I actually have a WXML team of UW undergrads right now who are thinking precisely about extending some of the results I'm about to describe, and hopefully use this homotopical perspective in order to pick off some classical problems. Anyway, a nice thing about transfer systems is that they're generated by covering relations. And from that, you can show that it's exactly the matchstick games, the legal configurations, that are the covering relations in a saturated transfer system on a rectangular lattice. And via that perspective, with Usman and Peter and Angelica, we were able to count the saturated transfer systems on a rectangular lattice. And, well, I already asked. I guess no one got this formula. So what are we looking at here? This is 1/2 of a particular sum. It alternates. And then we've got a Stirling number of the second kind, a factorial, and then this consecutive nth powers showing up. So it's a pretty wacky number, and I can tell you over that beverage a lengthy story about how this formula came about. An observation due to Igor Krij when I presented this work previously is that you can actually derive a really beautiful exponential generating function from the recurrences on which this closed formula are based. So there's a nice way to view it as well. I wrote down a few of the values that this takes, and if you had just decided to explicitly produce all the matchstick games here, you'd end up with this 58 million and change number. Okay, so this is a quick summary of everything that I talked about, and I'll scroll back to this during Q&A. But some questions that I'd like to pose, especially to the combinatorialists out there. Question 1, have these transfer systems been studied before? I cannot find them in the literature. I have looked pretty extensively. I have emailed Richard Stanley and anxiously awaiting his reply. I don't know. It seems like a relatively natural construction. There's some cool combinatorics underlying, but I haven't found them. I'm also very curious whether this connects to the generalized Catalan numbers that show up in cluster algebras and generalized dissociahedra and various things associated with Dynkin diagrams. And then, just sitting staring at us is this challenge to enumerate the Quillen model structures for other categories, for other lattices. So Boolean lattices seem like an interesting case, and of course many others. So I'll stop there and say thanks. Here's a bunch of references from which this work came. You can access all of it on my website here. I'll just briefly highlight. Today, I talked mostly about work from this paper with Balchin, Osorno, and Reutzheim, and also this paper with Balchin and McBrow. Ethan is a powerhouse of ideas, and we have 2 more papers out this summer that explicitly focus on the transfer system side of this and think back towards the equivariant homotopy theory. So again, I'll stop there, and I'm happy to take questions. Yeah. Yeah, Boolean algebras would be great. The case of saturated transfer systems on the Boolean poset. So one of the things that was listed in this theorem here is that they correspond to closure operators. So this is a little bit shy of a Kuratowski closure operator that would give you a topology. It's fewer conditions than that. But they have been studied like in the computer science literature, actually. And if I'm remembering correctly, the values are known for n between 0 and like 7. At that point, you're up in the billions or something. And then like no one has computed the 8th, just unknown, even for the saturated case. So kind of interesting. All right, pleasure seeing all of you. And again, I'm more than happy to speak more about this stuff in the future. So thank you.